Graphing a rational function. Before we begin, I want to go over something very briefly. A lot of the techniques we're using involve setting things equal to zero or plugging zero in. So I just want to go over, with a simple rational function, what will happen based on where the zero is. For example, if we have this rational function and I get a zero in the numerator, well, zero divided by anything except zero is going to give us a zero. On the other hand, if something ever causes the denominator to become zero, a chosen value of x, then we get something that does not even exist. That's very different than getting out a zero. And finally, if you plug in a zero for x, in this case, you get a 1/7. That's a number, that's a value. So where you place the zero or where you get a zero in the rational function really matters. We're going to go over graphing a rational function by going in depth into this example. We're going to create a sketch that'll be a rough picture of what this will look like. Just like last time, we're going to have our all work box here. We're going to place the conclusions of our different steps so that we can draw our picture. What are those steps? Well, step one is to get f of x in the lowest terms. We want to factor both the numerator and the denominator. Step two, find the zeros of the numerator. Step three, find the zeros of the denominator. Step four, determine the horizontal asymptote behavior. This takes the place of finding the end behavior with our polynomial functions. And then we have to compute additional points as necessary. So let's get started. So let's assume I'm trying to get this f of x in lowest terms, and I look at the numerator and I see a quadratic, and the factoring just jumps off the page at me. That's great. We have lots of tools for quadratics. Be sure to check your factoring, but I factored as x plus 2 times x plus 2. But then I'm working, and the degree 3 polynomial on the bottom is trickier. We don't have as many tools. I try factor by grouping, but I can't figure it out. Well, that's okay. You can always bring in all the stuff we were using to come up with the factorization from our graphing polynomials video. So we take that denominator and we apply the possible rational zeros to it. In this case, those are 1, -1, 3, and -3. We use synthetic division to test out one of those zeros, one of the possible zeros. We're going to try 1. Sure enough, it is a 0. So we get a factor of x minus 1 times x squared minus 2x minus 3 as a factorization. We work there with the remaining quadratic. Again, it's a quadratic, but let's assume I just can't see it. I'm going to apply the rational zeros again. I try 1 again in case it has multiplicity. Nope. So I try the next, -1. It works. It factors as x plus 1 times x minus 3. So now I have a factorization of f of x. This is the rational function in lowest terms. In this case, none of the factors canceled, but if they did, we would get a hole in the picture. Step 2. Let's find the zeros of the numerator. As we already factored it, this is actually going to be pretty quick. We take that numerator, set it equal to 0. By the zero factor property, either one of these factors being 0 would make the entire numerator 0. So x equals -2 is a 0 of the numerator polynomial with multiplicity 2. This means that -2 comma 0 is an x-intercept, and as it has multiplicity 2, the graph will touch or bounce. Step 3. Find the zeros of the denominator. Again, as we've already taken the time to factor it, it's going to be pretty quick to actually find those zeros. Zero factor property says if any one of these factors are 0, the whole thing would be 0. So I get x equal 1, x equal -1, and x equal 3 all as zeros of the denominator. However, recall that comment at the top of the video. The result here is very different. If the denominator becomes 0, we get something that does not exist. So 1, -1, and 3 are not in the domain of f of x. So these will actually create the vertical asymptotes. Be careful of the notation here. X equal 1, the value, the assignment of x to the value of 1 is a 0, whereas the vertical asymptote is a vertical line that has equation x equal 1, for example. Determine horizontal asymptote behavior. This test is unlike any of the tests we've seen before. It's very unique. I'm going to wipe away the factorization because this time I just want to focus on the function as it was given, because I'm going to need to look at the degrees. We assign the degree of the numerator polynomial to n. We assign the degree of the denominator polynomial to m. We want to compare these two. So in our example here, the numerator is degree 2, the denominator is degree 3. So we get n equals 2 and m equals 3. There are 3 cases to consider. If n is greater than m, there will be no horizontal asymptote. Comment, it is possible for there to be a slant asymptote. That will occur if n is exactly 1 larger than m. They could be equal. If they're equal, we get horizontal asymptote. So this is the y equals a value. It's a horizontal line. That line is the height of that line is determined by the leading coefficient of the numerator over the leading coefficient of the denominator. Final case, what if n were less than m? If this happens, we have a horizontal asymptote at the line y equals 0. In this case, 2 is less than 3, n is less than m, so we have a horizontal asymptote y equals 0. Now for the last step, compute additional points as necessary. Before we tackle this one, we actually need to get started on our picture a little bit to figure out what is necessary. I'm going to plot my x-intercept. Just like last time, I'm going to use an x at the x-intercept to help me indicate that this is going to be a bounce, not a cross. I draw my vertical asymptotes, one at -1, one at 1, and one at x equal 3. These are all vertical lines that I cannot cross or touch when I draw the picture. Remember, 1, -1, and 3 are not in the domain. Finally, my horizontal asymptote was at y equals 0. You'll note that I'm not putting it in the middle of the picture here because I can cross that horizontal asymptote just as I go to the far left and far right of the picture. I need to be approaching that asymptote. It's similar to our end behavior. So these green sections here flashing are the individual sections where I have questions about where the graph is between and beyond each one of those vertical asymptotes. So as I have 4 sections, I'm going to need 4 additional points at minimum. Let's take a look at that first section there. I need to know, am I stuck in the top quadrant there or the bottom? I pick any value that I want to test. In this case, I'm going to choose x equal -3. I'll plug this in, plug it into the factorized version of f of x, it goes faster, and I get -1/48. I'm going to plot it there with my purple point. Move on to the next section. Pick numbers that are easy to evaluate. We know that 0 is an easy number to do arithmetic with. So I'm going to pick x equals 0. Plug that in, and I get 4/3. Moving on to the next section, I'm going to pick x equal 2, plug that in, get out negative 16 over 3. Move on to the final section, going to plug in a 4, and I get 12/5. Plot that point. Now ready to zoom in on my picture. So I'm going to draw the part on the left side here. I want the line to approach that blue dotted line as it goes off the page. I need to go through that purple point, and I need to touch that green X. Next, that do not cross the x-axis anywhere, and I cannot cross that red dotted line. So this is a rough sketch. This is the picture I drew. The behavior could be different in between these known pieces of information, but this will suffice. Next, I move on to the next section. I need to go through that known point. I cannot cross the x-axis because we didn't find any x-intercepts there, and I cannot cross those vertical asymptotes. So I'm kind of caged in. So this is what I get. Same logic on the next part. I'm kind of boxed in below the x-axis there. So I'm just going to draw something that goes through that point that we know and goes down to negative infinity because I cannot pass those vertical asymptotes. Similar logic for the very final piece here, making sure that as I head to the far right of the page, I'm heading towards that horizontal asymptote. As you can see, the rough sketch here for this rational function is a very odd looking graph. So that's it for graphing rational functions. Just be sure to follow these 5 steps.